look up at the night sky on a clear evening, what you see stretching endlessly above you contains more stars than there are grains of sand on all the beaches of Earth. Each of those distant points of light is a sun, and many of them likely have planets orbiting around them. In our galaxy alone, there are over 400 billion stars. Beyond our galaxy, there are trillions more galaxies, each containing billions of their own stars. The numbers are staggering, the possibilities seem infinite. With such vast cosmic real estate, the idea that Earth is the only planet to harbour life seems almost impossible. Yet here we are, looking up at that same night sky, wondering why we seem to be so utterly alone. This is one of the most profound mysteries of our time. If the universe is teeming with potential for life, where is everybody? Why haven't we heard from them? Why haven't they found us? The silence from the cosmos is deafening, and it raises questions that challenge our understanding of life, intelligence, and our place in the universe. Scientists estimate that there could be billions of potentially habitable planets in our galaxy alone. Some of these worlds might have had billions of years longer than Earth to develop life and intelligence. If even a tiny fraction of these planets developed advanced civilizations, the galaxy should be buzzing with activity. Radio signals, space probes, massive engineering projects, something should have reached us by now. But the universe remains quiet. No alien radio broadcasts have been definitively detected. No spacecraft have landed on the White House lawn. No massive structures built by alien civilizations have been spotted around distant stars. The great silence persists, and it's both humbling and unsettling. This mystery has captivated scientists, philosophers, and dreamers for generations. It touches on fundamental questions about the nature of life itself. Are we truly alone? Or are we simply looking in the wrong places, in the wrong ways, or at the wrong times? Perhaps the answer lies not in the absence of alien life, but in the barriers that keep civilizations from finding each other across the vast distances of space and time. The search for extraterrestrial life is more than just a scientific endeavor. It's a quest to understand our own origins, our future, and our significance in the cosmic story. Every radio telescope pointed at the stars, every space probe launched into the void, every exoplanet discovered brings us closer to answering one of humanity's most enduring questions. As we embark on this journey through the theories, possibilities, and mysteries surrounding extraterrestrial life, we'll explore the scientific explanations for the Great Silence. We'll examine the challenges facing any civilization trying to communicate across interstellar distances, and we'll consider the possibility that the answer to our loneliness might be more complex and surprising than we ever imagined. The universe is vast and full of wonders we are only beginning to understand. Whether we are alone or part of a cosmic community we have yet to discover, the search itself reveals something profound about human nature, our curiosity, and our relentless drive to explore the unknown. The Great Silence may be telling us something important about the nature of intelligence, civilization, and survival in the cosmos. Tonight, when you look up at the stars, remember that you are gazing into the greatest mystery of our time. Somewhere out there, in the depths of space, the answer to our cosmic loneliness may be waiting to be discovered. To truly understand why we haven't found aliens yet, we must first grasp the sheer scale of the universe we inhabit. The numbers involved are so large that they challenge our ability to comprehend them, yet they are crucial to understanding the cosmic stage on which the drama of life unfolds. Our universe began 13.8 billion years ago with the Big Bang. In the time since, it has expanded to dimensions that boggle the mind. The observable universe, the part we can actually see, stretches 93 billion light years across. To put this in perspective, light from the most distant galaxies we can observe began its journey toward us when the universe was just a fraction of its current age. Within this vast expanse lies our own galaxy, the Milky Way. It's a spiral galaxy containing somewhere between 200 billion and 400 billion stars. Each of these stars is a sun, many larger and more luminous than our own. The Milky Way itself is just one galaxy among an estimated 2 trillion galaxies in the observable universe. Each galaxy contains billions or even trillions of stars. The total number of stars in the observable universe is estimated to be around 10 to the power of 24, a number so large it exceeds the total number of grains of sand on all the beaches and deserts on Earth. But stars are just the beginning of our cosmic inventory. Around many of these stars orbit planets, and it's on planets that we expect to find life as we know it. The discovery of exoplanets, planets orbiting stars other than our Sun, has revolutionized our understanding of how common planetary systems are in the universe. The first exoplanet orbiting a Sun-like star was discovered in 1995 by astronomers Michel Mayor and Didier Queloz. They found a planet called 51 Eridani b, a gas giant orbiting incredibly close to its star. This discovery shocked the astronomical community because it challenged everything we thought we knew about planetary formation. Here was a planet larger than Jupiter, but orbiting its star in just 4 days, closer than Mercury orbits our Sun. Since then, we've found thousands more exoplanets, each discovery adding to our understanding of how diverse planetary systems can be. NASA's Kepler Space Telescope, launched in 2009, discovered over 2,600 confirmed exoplanets during its mission. The telescope worked by watching for tiny dips in starlight that occur when a planet passes in front of its star, a method called the transit technique. The Transiting Exoplanet Survey satellite, launched in 2018, continues this work, finding new worlds at an unprecedented rate. TESS has already discovered thousands of planet candidates, and new confirmations are announced regularly. The James Webb Space Telescope, which began operations in 2022, has taken exoplanet science to the next level by analyzing the atmospheres of distant worlds. What's remarkable about these discoveries is not just their number, but their incredible diversity. We've found planets that challenge our imagination and expand our understanding of what's possible in the universe. There are planets larger than Jupiter orbiting closer to their stars than Mercury orbits our Sun. These hot Jupiters, as they're called, have surface temperatures reaching thousands of degrees Celsius. We've discovered planets where it rains molten glass sideways at speeds of 7,000 kilometers per hour. HD 189733b is one such world, where the temperature reaches over 1,000 degrees Celsius, and the winds are so fierce they could shred any spacecraft we might send there. On this planet, the glass rain is created by silicate particles in the atmosphere that condense and fall as the planet rotates. There are planets made almost entirely of diamond, worlds where the pressure and temperature have compressed carbon into crystalline structures. We found planets orbiting dead stars, called white dwarfs, somehow surviving the death of their host star. There are planets with multiple suns, where the sky would be filled with different colored stars rising and setting at different times. Some planets orbit so close to their stars that they're being slowly vaporized, leaving trails of gas behind them like cosmic comets. Others are so far from their stars that they're essentially frozen wastelands, colder than the most frigid places on Earth. We found planets where the day side is hot enough to melt metal, while the night side is frozen solid, creating permanent twilight zones where the temperature might be just right for liquid water. But among all these exotic worlds, we've also found planets that seem surprisingly familiar. These are the planets that orbit within what astronomers call the habitable zone, sometimes known as the Goldilocks zone. This is the region around a star where liquid water can exist on a planet's surface, not too hot and not too cold, but just right for life as we know it. The habitable zone varies depending on the type of star. around cooler, smaller stars like red dwarfs, the habitable zone is much closer to the star. Red dwarfs are the most common type of star in our galaxy, making up about 75% of all stars. They're much smaller and dimmer than our Sun, but they also live much longer, potentially providing stable conditions for billions of years, longer than Sun-like stars. Around hotter, larger stars, the habitable zone extends much farther out. These massive stars burn through their fuel quickly and don't live long enough for complex life to develop on their planets. Our Sun represents something of a middle ground, large enough to provide plenty of energy, but small enough to live for about 10 billion years, giving life plenty of time to evolve. Our Earth sits comfortably in the middle of our Sun's habitable zone, where water remains liquid and life can flourish. But we've discovered that the habitable zone concept is more complex than originally thought. Planets can have liquid water outside the traditional habitable zone if they have thick atmospheres that trap heat, or if they're heated by tidal forces from nearby massive planets. Scientists estimate that there could be as many as 11 billion Earth-sized planets in habitable zones around Sun-like stars in our galaxy alone. When we include planets around other types of stars, the number becomes even larger. Some estimates suggest there could be 40 billion potentially habitable planets in the Milky Way. But habitability depends on more than just distance from a star. A planet needs to have the right mass to hold onto its atmosphere, the right composition to support liquid water, and the right magnetic field to protect it from harmful radiation. It needs to be in a stable orbit that doesn't take it too close to or too far from its star over time. The planet also needs to be in the right location within the galaxy. Too close to the galactic center, and the radiation from densely packed stars and black holes might sterilize any life that tries to develop. Too far from the center, and there might not be enough heavy elements to form rocky planets in the first place. Consider what this means for the possibility of life in the universe. If even a tiny fraction of these potentially habitable planets developed life, and if even a smaller fraction of those developed intelligent life, our galaxy should be teeming with civilizations. Some of these civilizations might have had billions of years longer than us to develop technology and expand into space. The age of the universe gives us another perspective on this puzzle. Our Sun is relatively young compared to many stars in the galaxy. It formed about 4.6 billion years ago, when the universe was already over 9 billion years old. There are stars in our galaxy that are more than 13 billion years old, nearly as old as the universe itself. This means that planetary systems could have formed and evolved for billions of years before our solar system even existed. The first generation of stars that formed after the Big Bang were composed almost entirely of hydrogen and helium. These stars lived fast and died young, exploding as supernovae and scattering heavier elements into space. It took several generations of stars to create enough heavy elements like carbon, oxygen, and silicon to form rocky planets like Earth. But even accounting for this delay, there could have been Earth-like planets forming as early as 10 billion years ago. If life developed on any of these ancient worlds, it would have had an enormous head start on us, a civilization that began its technological development just 1 billion years before us would be incomprehensibly advanced by our standards. The scale of technological advancement possible over such time spans is difficult to imagine. Consider that human civilization has existed for only about 10,000 years, and our technological civilization for just a few hundred years. We went from the first powered flight by the Wright brothers in 1903 to landing on the moon in 1969, just 66 years later. We developed computers that once filled entire rooms into devices that fit in our pockets in just a few decades. What might a civilization accomplish with millions of times longer to develop? Such ancient civilizations might have technologies that seem like magic to us. They might have learned to harness the energy of entire stars, building massive structures called Dyson spheres that capture all the energy a star produces. They might have mastered faster than light travel, allowing them to explore the galaxy in timeframes that make sense for living beings. They might have learned to manipulate matter at the quantum level, creating materials with properties we can't imagine. They might have developed artificial intelligence far beyond our current capabilities, or learned to upload their consciousness into vast computer networks that could last for millions of years. They might have spread across the galaxy, establishing colonies around countless stars. With enough time, they could have transformed entire star systems to suit their needs, moving planets, adjusting star output, or building artificial habitats that dwarf anything we can conceive. Yet despite all these possibilities, despite the vast number of potentially habitable worlds, despite the billions of years available for life to develop and spread, we see no signs of these advanced civilizations. The galaxy appears empty of the obvious signatures we might expect from a thriving community of intelligent species. This absence is particularly puzzling when we consider how easily detectable some activities of advanced civilizations might be. If aliens were building megastructures around stars to capture their energy, we should be able to detect the unusual dimming patterns these structures would create. We've actually looked for these signatures, studying the light curves of hundreds of thousands of stars, but haven't found any convincing evidence of artificial structures. If they were using powerful radio transmitters for communication, we might be able to eavesdrop on their signals. Radio waves travel at the speed of light and can cross vast distances of space without significant degradation. A sufficiently powerful transmitter could be detected by our radio telescopes from thousands of light years away. If they were launching massive space missions, we might detect the infrared signatures of their spacecraft. Large spacecraft would need to radiate away excess heat, creating infrared signatures that our space telescopes could potentially detect. We've looked for these signatures as well, but haven't found any convincing evidence of alien spacecraft. The silence becomes even more mysterious when we consider that space travel, while challenging, is not impossible. Even with our current technology, we could theoretically send robotic probes to nearby star systems. It would take decades or centuries for them to arrive, but it's within the realm of possibility with technology we understand today. A sufficiently advanced civilization could send probes throughout the galaxy, even if they never developed faster than light travel. These probes wouldn't need to carry living beings, just the intelligence and technology needed to explore and report back. They could be powered by fusion reactors, solar sails, or other advanced propulsion systems. Some scientists have calculated that a civilization could explore the entire galaxy using self-replicating probes in just a few million years. These probes would travel to a star system, use the materials there to build copies of themselves, and then send these copies on to other star systems. Even traveling at just 1% the speed of light, this process could map every star in the galaxy in a relatively short time from a cosmic perspective. The mathematics of this galactic exploration are straightforward. With 400 billion stars in our galaxy and probes that can replicate themselves at each star system, the entire galaxy could be explored in about 1 million years. This assumes the probes travel at 1% the speed of light and take about 1,000 years to build copies of themselves at each destination. 1 million years might seem like a long time to us, but it's just a blink of an eye in cosmic terms. The galaxy is over 13 billion years old. If any civilization had started such an exploration program even 1 billion years ago, every star system in the galaxy would have been visited many times over by now. The fact that we see no evidence of such exploration is deeply puzzling. Where are the alien artifacts in our solar system? Where are the signs of ancient visitations? Where are the probes monitoring our development? We've explored much of our solar system with spacecraft and telescopes, but we've found no evidence of alien technology anywhere. The absence of any such evidence suggests either that we are alone, or that the challenges facing spacefaring civilizations are far greater than we imagine. Perhaps interstellar travel is so difficult that even advanced civilizations find it prohibitively expensive or dangerous. Perhaps there are physical laws we don't understand that make faster than light travel impossible and slower than light travel impractical. Perhaps the answer lies not in the absence of alien life, but in the barriers that prevent us from detecting it. The distances between stars are so vast that even advanced civilizations might find it difficult to maintain contact across interstellar space. The energy requirements for interstellar travel are enormous, and the timescales involved are daunting even for long-lived species. Or perhaps alien civilizations are out there, but they are so different from us that we don't recognize their activities as signs of intelligence. They might communicate using methods we haven't discovered, or they might have interests and goals so alien to us that their activities are invisible to our searches. The vastness of the universe, which seems to guarantee the existence of alien life, might also be the very thing that keeps us isolated from it. Space is not just big, it's unimaginably, incomprehensibly big. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. Even traveling at the speed of light, it would take over 4 years to reach it. With our current technology, it would take tens of thousands of years. The distances involved create barriers that might be insurmountable, even for advanced civilizations. Light speed is the ultimate speed limit in the universe, according to Einstein's theory of relativity. While there are theoretical concepts like wormholes and warp drives that might allow faster than light travel, these remain purely speculative and may be impossible to achieve in practice. In this vast cosmic ocean, intelligent life might be like islands scattered across an endless sea. Each island might be teeming with life and activity, but the distances between them are so great that they remain forever isolated from each other. We might be one such island, looking out across the vast emptiness, wondering if anyone else is out there looking back. The scale of the universe is both inspiring and humbling. It suggests that we are part of something much larger than ourselves, a cosmic story that spans billions of years and countless worlds. At the same time, it reminds us of how small and isolated we are in the grand scheme of things. The very vastness that makes alien life seem inevitable might also make contact with that life nearly impossible. In the summer of 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory when the conversation turned to reports of UFO sightings that had been making headlines. The scientists were discussing the possibility of faster-than-light travel and whether aliens might be visiting Earth. As they walked to lunch, they joked about the flying saucer reports and the likelihood of alien visitation. Once seated at the lunch table, the conversation moved on to other topics. But then, out of nowhere, Fermi suddenly exclaimed, "But where is everybody?" His colleagues immediately understood what he meant. Given the vast age of the universe, the billions of stars in our galaxy, and the high probability that many of them host planets, alien civilizations should be common. Some of these civilizations should have developed space travel millions or billions of years ago. So where are they? This simple question has become known as the Fermi paradox, and it represents one of the most profound puzzles in science. The paradox can be stated simply. The universe appears to be vast and old enough that intelligent life should be common, yet we see no evidence of it anywhere. This contradiction between expectation and observation has puzzled scientists for over 70 years. The paradox becomes even more striking when we consider the numbers involved. Our galaxy is approximately 13.6 billion years old. The first stars capable of hosting rocky planets formed about 10 billion years ago. If we assume that life can develop on suitable planets given enough time, then there has been ample opportunity for countless civilizations to arise and spread throughout the galaxy. Let's consider a conservative estimate. Suppose only 1 in a million suitable planets develops intelligent life, and suppose only 1 in a million of those civilizations develops space travel. Even with these incredibly conservative assumptions, our galaxy should still host hundreds of spacefaring civilizations. Some of these should have developed millions or billions of years before us. The timescales involved make the paradox even more puzzling. As we discussed earlier, a civilization could explore the entire galaxy using self-replicating probes in just a few million years. This is an incredibly short time span compared to the age of the galaxy. If any civilization had started such an exploration program even a billion years ago, every star system in the galaxy would have been visited thousands of times over. Yet we see no evidence of such visitation. Our solar system shows no signs of alien artifacts or ongoing monitoring. Our searches for radio signals from alien civilizations have turned up nothing definitive. The galaxy appears to be empty of the obvious signatures we might expect from a thriving community of intelligent species. This absence of evidence has led scientists to propose numerous explanations for the Fermi paradox. Each explanation attempts to resolve the contradiction between the high probability of alien life and the apparent absence of any evidence for it. These explanations fall into several broad categories, each with its own implications for our understanding of life in the universe. One of the most sobering explanations is the rare Earth hypothesis. This idea suggests that while simple life might be common in the universe, complex life like that found on Earth is extraordinarily rare. The hypothesis argues that Earth occupies a unique position in the galaxy and has experienced a unique combination of circumstances that made complex life possible. According to this hypothesis, Earth benefits from a rare combination of factors that are essential for complex life. We orbit a star that is neither too large nor too small, providing stable energy output for billions of years. We have a large moon that stabilizes our planet's rotation and creates tides that may have helped early life develop. We have a strong magnetic field that protects us from harmful cosmic radiation. Our planet has plate tectonics, which recycles carbon and maintains a stable climate over geological timescales. We have a massive planet, Jupiter, in our outer solar system that acts as a gravitational vacuum cleaner, sweeping up comets and asteroids that might otherwise bombard Earth. We're located in a quiet region of the galaxy, far from the chaotic center where radiation levels would be lethal to life. The rare Earth hypothesis suggests that while many planets might develop simple, single-celled life, the jump to complex multicellular life requires such a specific combination of factors that it happens extremely rarely. On Earth, it took over 3 billion years for complex life to develop, and the process required numerous unlikely events and near misses. For example, complex life on Earth depends on mitochondria, the powerhouses of our cells. These organelles were once independent bacteria that somehow became incorporated into larger cells in a process called endosymbiosis. This event was so improbable that it may have happened only once in Earth's history, yet it was essential for the development of complex life. The development of multicellular life required another series of unlikely events. Cells had to learn to cooperate rather than compete, to specialize their functions, and to form complex structures. This process took hundreds of millions of years and might have been derailed by numerous catastrophic events. Even after multicellular life developed, the path to intelligence was far from guaranteed. Earth has experienced several mass extinction events that nearly wiped out all life on the planet. The extinction that killed the dinosaurs 66 million years ago was just one of many such events. Each time, life had to recover and evolution had to start over in many ways. Intelligence itself appears to be a recent and possibly rare development. Humans have existed for only about 300,000 years, and our technological civilization for just a few hundred years. From the perspective of Earth's 4.6 billion year history, intelligence appeared only in the last few moments. The rare Earth hypothesis suggests that each step in the development of complex, intelligent life is so improbable that even in a galaxy with billions of planets, we might be the only ones to have made it this far. This would explain why we see no evidence of alien civilizations. They simply don't exist in any significant numbers. Another explanation for the Fermi paradox is the Great Filter hypothesis. This idea suggests that somewhere in the development from simple chemistry to spacefaring civilization, there is a step that is so difficult that it acts as a filter, preventing most life from advancing beyond a certain point. This filter could be located anywhere in the evolutionary chain, from the origin of life itself to the development of intelligence, to the creation of technological civilization. If the Great Filter is behind us, then we are among the lucky few who have managed to pass through it. This would be good news for humanity's future, as it would suggest that we've already overcome the most difficult challenges in our development. However, it would also suggest that we are likely alone in the galaxy, as most other potential civilizations would have been stopped by the same filter that we somehow managed to pass. If the Great Filter is ahead of us, then we are in grave danger. This would suggest that while life might be common in the universe, something prevents most civilizations from advancing much beyond our current level. Perhaps advanced civilizations inevitably destroy themselves through warfare, environmental collapse, or some other catastrophic event. Perhaps there are physical or technological barriers that make interstellar travel impossible or impractical. The Great Filter could also be a combination of multiple difficult steps, each of which eliminates a large percentage of potential civilizations. For example, the development of life might be moderately difficult, the development of intelligence might be very difficult, and the development of stable technological civilization might be nearly impossible. Some scientists have suggested that the Great Filter might be the development of intelligence itself. While life appears to be relatively robust and adaptable, intelligence might be an evolutionary dead end. On Earth, intelligence has developed only once in the human lineage. Many other species have evolved complex behaviors and even tool use, but none have developed the kind of abstract reasoning and technological capability that characterizes human intelligence. Intelligence might be costly from an evolutionary perspective. Large brains require enormous amounts of energy to maintain. Human brains consume about 20% of our total energy, far more than the brains of other animals. This energy cost might make intelligence a poor evolutionary strategy in most environments. Furthermore, intelligence might be accompanied by traits that are ultimately self-destructive. The same cognitive abilities that allow us to develop technology also allow us to create weapons, to exploit our environment unsustainably, and to engage in complex social conflicts. Perhaps most intelligent species destroy themselves shortly after developing advanced technology. Another possibility is that the Great Filter is related to the development of technological civilization itself. Even if intelligence develops, the step from intelligence to technology might be extremely difficult. On Earth, technological civilization developed only once, in the human species. Many other intelligent species, such as dolphins and great apes, have not developed technology beyond simple tool use. The development of technology might require not just intelligence, but a very specific combination of intelligence, manipulative appendages, social organization, and environmental circumstances. Perhaps most intelligent species lack the physical capability to manipulate their environment in ways that lead to technology development. Technology development might also require specific environmental conditions. On Earth, the development of metallurgy was essential for advanced technology, but this required access to metal ores and the ability to create high-temperature fires. An intelligent aquatic species might find it difficult to develop metallurgy or other technologies that require fire. The social organization required for technological civilization might also be extremely rare. Technology development requires cooperation between many individuals, the accumulation of knowledge across generations, and the ability to engage in complex planning and organization. Perhaps most intelligent species lack the social structures necessary for technological development. Even if technological civilization develops, it might be inherently unstable. The same technologies that allow a species to manipulate their environment also give them the power to destroy themselves. Nuclear weapons, biological weapons, artificial intelligence, and environmental destruction all pose existential risks to technological civilizations. Perhaps the great filter is the challenge of developing technology while avoiding self-destruction. This would explain why we see no evidence of alien civilizations. They all destroy themselves shortly after developing advanced technology. This interpretation of the great filter is particularly sobering, as it suggests that our own civilization might be doomed to the same fate. Another explanation for the Fermi paradox is that alien civilizations are simply too far away for us to detect them. While our galaxy contains billions of stars, it is also incredibly vast. The distances between stars are so great that even advanced civilizations might find it difficult to communicate across interstellar space. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. This means that even a radio signal traveling at the speed of light would take over 4 years to reach us from the nearest star. Signals from more distant stars would take proportionally longer to arrive. The problem becomes even more severe when we consider that alien civilizations might not be distributed evenly throughout the galaxy. Life might be more common in certain regions, such as areas with the right concentration of heavy elements, or regions far from the chaotic galactic center. If most alien civilizations are concentrated in regions far from our solar system, we might be too isolated to detect them. Even if alien civilizations are trying to communicate, we might not be listening at the right time or in the right way. Radio signals from alien civilizations would need to be directed toward our solar system and broadcast at a time when we are technologically capable of receiving them. Given the vast timescales involved, the window for successful communication might be very small. Furthermore, advanced civilizations might use communication methods that we haven't discovered or can't detect. They might use neutrinos, gravitational waves, or other exotic forms of communication that we are only beginning to understand. They might encode their messages in ways that we don't recognize as artificial signals. The inverse square law also works against us in detecting alien signals. As a signal travels through space, it spreads out in all directions, becoming weaker with distance. A signal that is detectable from 1 light-year away might be too weak to detect from 10 light-years away. This means that only the most powerful alien transmitters would be detectable over interstellar distances. Another possibility is that alien civilizations exist, but are deliberately avoiding contact with us. This explanation, sometimes called the Zoo hypothesis, suggests that advanced civilizations are aware of our existence, but choose not to interfere with our development. They might observe us from a distance, much like we observe animals in a zoo or nature preserve. The Zoo hypothesis suggests that there might be a kind of galactic ethics that prevents advanced civilizations from interfering with less advanced ones. This non-interference principle might be similar to the Prime Directive in Star Trek, which prohibits interference with primitive civilizations. Advanced aliens might believe that contact with us would be harmful to our development, either by providing us with technology we're not ready for or by disrupting our natural cultural evolution. This explanation would resolve the Fermi paradox by suggesting that alien civilizations are out there but are intentionally remaining hidden from us. They might have advanced technology that makes their activities invisible to our searches, or they might simply be very good at avoiding detection. The Zoo hypothesis raises interesting questions about the nature of intelligence and civilization. If it's true, it suggests that the development of advanced technology is accompanied by a kind of ethical maturity that prevents the exploitation or interference with less advanced species. This would be encouraging for the future of our own civilization, as it would suggest that survival to advanced status requires the development of peaceful and ethical behavior. However, the zoo hypothesis also faces some challenges. It requires that all advanced civilizations agree to maintain the quarantine around Earth. Even if most civilizations are ethical and non-interfering, it would take only one rogue civilization to break the quarantine and make contact with us. The fact that no such contact has occurred suggests either that the quarantine is absolute or that there are no civilizations out there to maintain it. These various explanations for the Fermi paradox each have different implications for our understanding of life in the universe and our place within it. The rare Earth hypothesis suggests that we are incredibly special, perhaps the only intelligent life in the galaxy. The Great Filter hypothesis suggests that intelligence is common but short-lived. The distance explanation suggests that alien civilizations exist but are too far away to contact. The zoo hypothesis suggests that aliens are nearby but choosing not to reveal themselves. Each explanation is consistent with our current observations, but they lead to very different conclusions about the nature of life and intelligence in the universe. The truth might involve elements of several of these explanations, or it might be something entirely different that we haven't yet considered. The Fermi paradox remains one of the most profound questions in science because it touches on fundamental issues about the nature of life, intelligence, and our place in the cosmos. The answer to Fermi's simple question, "Where is everybody?" will likely reshape our understanding of the universe and our role within it. Until we find that answer, we remain alone with our questions, looking up at the stars and wondering if anyone is looking back. The Great Filter represents one of the most chilling possible explanations for the Fermi paradox. This concept suggests that somewhere along the evolutionary path from simple chemistry to spacefaring civilization, there exists a step so monumentally difficult that it acts as an almost insurmountable barrier. This filter is so effective that it prevents the vast majority of potential life from ever reaching the point where it could spread across the galaxy and make contact with other civilizations. The implications of the Great Filter are profound and unsettling. If such a filter exists, it means that despite the billions of potentially habitable planets in our galaxy, very few ever develop into the kind of advanced civilizations we might hope to encounter. The filter could be located anywhere along the developmental chain, from the very first spark of life to the final challenge of becoming a stable, long-lived technological civilization. Understanding where this filter might be located is crucial for assessing both the likelihood of finding alien life and the probability of our own long-term survival. If the Great Filter lies behind us in our evolutionary past, then we are among the incredibly rare and fortunate few who have managed to pass through it. This would suggest that we are likely alone in the galaxy, but it would also indicate that our future prospects are relatively bright. However, if the Great Filter lies ahead of us, then we face a terrifying possibility. It would mean that while life and even intelligence might be relatively common in the universe, something prevents almost all civilizations from progressing much beyond our current level of development. Perhaps they destroy themselves through war, environmental collapse, or technological catastrophe. Perhaps they encounter some fundamental barrier that makes further progress impossible. Let's examine the various stages where the Great Filter might be located, starting from the very beginning of the journey from chemistry to civilization. Each stage represents a potential bottleneck that could serve as the filter that keeps the galaxy seemingly empty of advanced life. The first possible location for the Great Filter is the emergence of life itself. While we tend to think of life as a natural consequence of the right chemical conditions, the transition from non-living molecules to self-replicating organisms is actually an incredibly complex process that we still don't fully understand. On Earth, life appears to have emerged relatively quickly after conditions became suitable. The planet formed about 4.6 billion years ago, and the earliest evidence of life dates back to about 3.8 billion years ago. This suggests that given the right conditions, life might emerge relatively easily. However, this could be misleading. The early Earth was a very different place from the planet we know today. The atmosphere contained virtually no oxygen. The surface was bombarded by asteroids and comets, and volcanic activity was far more intense than today. Despite these harsh conditions, life somehow managed to emerge and take hold. The process of abiogenesis, the transition from non-living chemistry to living organisms, requires an extraordinary series of chemical reactions to occur in just the right sequence. Simple organic molecules must somehow organize themselves into increasingly complex structures, eventually leading to self-replicating systems that can evolve and adapt. Scientists have proposed various scenarios for how this might have happened. One possibility is that life began in hydrothermal vents on the ocean floor, where hot, mineral-rich water provided the energy and chemical building blocks necessary for complex chemistry. Another possibility is that life began in shallow pools that went through cycles of drying and wetting, concentrating organic molecules and promoting chemical reactions. RNA, a molecule similar to DNA but simpler in structure, might have played a crucial role in the emergence of life. RNA can both store genetic information and catalyze chemical reactions, making it a prime candidate for the first self-replicating molecule. However, getting from simple organic molecules to functional RNA is still an enormous leap that requires many intermediate steps. The fact that we have only one example of life emerging here on Earth makes it difficult to assess how likely this process actually is. If abiogenesis is the great filter, then life itself might be extraordinarily rare in the universe. Every planet might need to win an incredible chemical lottery for life to begin, and most planets might simply never hit the jackpot. If this is the case, then Earth might be one of very few planets in the galaxy where life has ever emerged. This would explain the silence we observe, but it would also suggest that we are incredibly special and precious, as possibly the only living world in our cosmic neighborhood. The second potential location for the Great Filter is the development of complex cells. For about 2 billion years after life first emerged on Earth, all organisms were prokaryotes, simple cells without nuclei or other complex internal structures. These early life forms were essentially bacteria and archaea, single-celled organisms that could reproduce and evolve, but remained relatively simple. The jump from prokaryotic cells to eukaryotic cells, which have nuclei and complex internal structures, was a monumental leap in the history of life. This transition, which occurred about 2 billion years ago, was essential for the later development of multicellular life and everything that followed. The key event in this transition was endosymbiosis, the process by which one cell engulfed another and they began living together in a mutually beneficial relationship. The engulfed cell eventually became the mitochondria, the powerhouse organelles that provide energy for complex cellular processes. In plant cells, a similar process led to the incorporation of chloroplasts, the organelles responsible for photosynthesis. This endosymbiotic event appears to have happened only once in Earth's history, suggesting that it might be an extraordinarily rare occurrence. The process required one cell to engulf another without digesting it, and then for both cells to adapt to living together in a stable, long-term relationship. The chances of this happening might be vanishingly small. Without mitochondria, complex life as we know it would be impossible. These organelles provide the energy necessary for complex cellular processes and allow cells to grow much larger than would otherwise be possible. If endosymbiosis is the great filter, then most planets might be stuck forever in the prokaryotic stage, never developing the complex cells necessary for multicellular life. The third potential location for the great filter is the emergence of multicellular life. Even after eukaryotic cells developed, it took another billion years for multicellular organisms to appear. This transition required cells to give up their independent existence and begin cooperating in complex ways. Multicellularity required the evolution of mechanisms for cell-to-cell communication, cell specialization, and coordinated development. Cells had to learn to sacrifice themselves for the good of the organism, to differentiate into different types with different functions, and to organize themselves into complex three-dimensional structures. This transition happened several times independently on Earth, suggesting that it might not be as rare as some of the earlier transitions. However, the development of complex multicellular organisms with differentiated tissues and organs happen much less frequently and might represent a significant barrier. The fourth potential location for the Great Filter is the development of intelligence. While multicellular life has been around for hundreds of millions of years and has produced an incredible diversity of organisms, intelligence comparable to that of humans has evolved only once. This suggests that intelligence might be an extremely rare evolutionary outcome. Intelligence, as we understand it, requires a large, complex brain capable of abstract reasoning, planning, and problem solving. The human brain consumes about 20% of our total energy, making it incredibly expensive from a metabolic standpoint. This high energy cost might make intelligence an evolutionary luxury that most species simply cannot afford. Furthermore, intelligence might not always be advantageous for survival. Many species have thrived for millions of years without developing significant intelligence. Sharks have remained essentially unchanged for hundreds of millions of years, and bacteria have been successful for billions of years without any intelligence at all. The evolution of intelligence might require a very specific set of environmental pressures and evolutionary circumstances. On Earth, intelligence appears to have developed in response to social pressures and the challenges of living in complex social groups. The ability to cooperate, communicate, and outcompete other groups might have been the driving force behind the evolution of human intelligence. If intelligence is the Great Filter, then most planets might develop complex life, but never produce species capable of reasoning about their universe or developing technology. They might be filled with the equivalent of Earth's Cambrian period, with complex multicellular life, but no species approaching human-level intelligence. The fifth potential location for the Great Filter is the development of technological civilization. Even if intelligence evolves, the step from intelligence to technology capable of space travel and interstellar communication might be extraordinarily difficult. On Earth, technological civilization is a very recent development. Humans have existed as a species for about 300,000 years, but we've had agriculture for only about 10,000 years and industrial technology for just a few hundred years. Our ability to communicate across interstellar distances has existed for less than a century. The development of technology requires not just intelligence, but a very specific combination of other factors. A species needs manipulative appendages capable of precise tool use. They need access to materials like metals that can be shaped into tools and machines. They need the ability to control fire or some other energy source for metallurgy and manufacturing. The species must also develop complex social organization, capable of accumulating knowledge across generations and coordinating large-scale projects. They need written language or some other method of preserving and transmitting information. They need economic systems capable of supporting individuals who specialize in research and development rather than immediate survival needs. Perhaps most importantly, they need to avoid destroying themselves during the dangerous period when they first develop powerful technologies. The same intelligence that allows a species to develop technology also gives them the ability to create weapons of mass destruction, to exploit their environment unsustainably, and to engage in large-scale warfare. On Earth, we've come perilously close to self-destruction several times. The Cold War brought us to the brink of nuclear annihilation on multiple occasions. Climate change threatens to disrupt our civilization through environmental collapse. The development of artificial intelligence, biotechnology, and other advanced technologies brings new existential risks that we're only beginning to understand. If technological self-destruction is the great filter, then intelligence might be common in the universe, but technological civilizations might have very short lifespans. They might typically destroy themselves within a few centuries of developing industrial technology, explaining why we don't see evidence of advanced alien civilizations. This interpretation of the Great Filter is particularly sobering because it suggests that our own civilization is currently passing through the most dangerous period in our existence. We're developing incredibly powerful technologies while still retaining many of the aggressive and short-sighted instincts that helped our species survive in a more primitive environment. The sixth potential location for the Great Filter is the challenge of becoming a stable, long-lived civilization capable of interstellar expansion. Even if a species manages to develop advanced technology without destroying itself, it might face additional challenges in becoming a truly spacefaring civilization. Interstellar travel presents enormous technical challenges that might be impossible to overcome. The distances between stars are so vast that even traveling at a significant fraction of the speed of light would require enormous amounts of energy and take decades or centuries to complete. The energy requirements for accelerating a spacecraft to even 1% of the speed of light are staggering. Perhaps there are fundamental physical laws that make faster than light travel impossible, leaving civilizations forever trapped in their home star systems. Even if they can send robotic probes to other stars, the time delays involved in communication might make it impossible to maintain a coherent interstellar civilization. Alternatively, advanced civilizations might face social or psychological barriers to interstellar expansion. The resources required for such projects might be so enormous that they're difficult to justify to democratic societies focused on immediate needs. The timescales involved might be longer than any political or social system can maintain focus. Advanced civilizations might also face the challenge of technological stagnation. They might reach a point where further technological progress becomes increasingly difficult, either because they've discovered all the fundamental physical laws, or because the complexity of their technology has reached the limits of what their intelligence can manage. Another possibility is that advanced civilizations deliberately choose not to expand into space. They might decide that the resources and effort required for interstellar expansion are better spent on improving life in their home system. They might develop virtual reality technologies so advanced that they prefer to explore simulated universes rather than the real one. The Great Filter might also be located in the far future, representing challenges that our civilization has not yet encountered. Perhaps there are threats or limitations that only become apparent once a civilization reaches a certain level of advancement. These could include encounters with other advanced civilizations that are hostile, the discovery of fundamental limits to growth and expansion, or existential risks that emerge from advanced technologies. The location of the Great Filter has profound implications for our search for extraterrestrial life and our assessment of our own future prospects. If the filter is behind us, then we should not expect to find evidence of alien civilizations, but we can be optimistic about our own long-term survival. If the filter is ahead of us, then we might find evidence of alien life at earlier stages of development, but we should be deeply concerned about our own future. Recent discoveries have provided some clues about where the Great Filter might be located. The detection of organic molecules in space and on other planets suggests that the basic chemistry of life might be relatively common. The rapid emergence of life on early Earth suggests that abiogenesis might not be as difficult as once thought. However, the apparent rarity of complex life in Earth's history and the late emergence of intelligence suggests that these might be more likely candidates for the Great Filter. The fact that technological civilization emerged only once on Earth and only very recently suggests that this transition might be particularly difficult. The Great Filter concept forces us to confront uncomfortable questions about our own future. Are we among the rare few who have successfully passed through the most difficult challenges facing life in the universe? Or are we about to encounter barriers that have stopped countless other civilizations before us? The answer to these questions will determine not only whether we ever find evidence of alien life, but whether our own species has a long-term future among the stars. Understanding the Great Filter is more than an academic exercise. It's a crucial element in assessing existential risks and planning for our civilization's future. If we can identify where the filter is most likely to be located, we can better prepare for the challenges ahead and work to ensure that we become one of the rare civilizations that successfully passes through all the barriers between chemistry and the stars. In 1960, a young astronomer named Frank Drake pointed a radio telescope at two nearby stars and listened for signals that might indicate the presence of intelligent alien life. This marked the beginning of the modern search for extraterrestrial intelligence, known as SETI. For the first time in human history, we had developed technology sophisticated enough to potentially detect communications from alien civilizations across interstellar distances. Drake's initial experiment, called Project Ozma, monitored the stars Tau Ceti and Epsilon Eridani for several months. He chose these targets because they were relatively nearby, about 11 and 10.5 light-years away respectively, and because they were similar to our Sun in age and composition. The project detected no alien signals, but it established the methodology that would guide SETI research for decades to come. The fundamental premise behind SETI is elegant in its simplicity. If alien civilizations exist and have developed radio technology, they might be broadcasting signals into space, either intentionally to communicate with other civilizations or unintentionally as a byproduct of their technology. These radio waves would travel at the speed of light across vast distances, potentially reaching Earth, where we could detect them with sensitive radio telescopes. Radio waves are ideal for interstellar communication because they can travel enormous distances through space without significant degradation. Unlike optical light, radio waves are not easily blocked by dust and gas in interstellar space. They also require relatively little energy to produce and can carry complex information encoded in their frequency and amplitude patterns. The challenge, however, is enormous. Space is vast, and alien signals would be incredibly weak by the time they reached Earth. A radio transmission from even the nearest star would arrive at Earth with a power level billions of times weaker than that of a cell phone. Detecting such signals requires extraordinarily sensitive equipment and sophisticated data processing techniques. Moreover, we don't know what frequency aliens might use for their transmissions. The radio spectrum spans a huge range of frequencies, from a few kilohertz to hundreds of gigahertz. Searching this entire range for alien signals is like looking for a needle in a cosmic haystack, except we don't know what the needle looks like, or even if it exists. Despite these challenges, SETI researchers have developed systematic approaches to the search. They focus on specific frequency ranges that seem most promising for interstellar communication. One such range is around 1421 megahertz, the frequency at which hydrogen atoms emit radio waves. This frequency is significant because hydrogen is the most abundant element in the universe, making it a natural choice for a universal communication frequency. Another promising frequency range is around 1665 megahertz, where hydroxyl molecules emit radio waves. Together with the hydrogen line, this forms what scientists playfully call the water hole, since hydrogen and hydroxyl combine to form water. The idea is that any civilization that understands chemistry would recognize the significance of these frequencies. The search strategy has evolved dramatically since Drake's early experiments. Modern SETI projects use arrays of radio telescopes working together to survey millions of stars simultaneously. The Allen Telescope Array in California, for example, consists of 42 individual radio dishes that work together as a single, highly sensitive instrument. When fully operational, It can monitor thousands of stars at the same time across multiple frequency bands. Breakthrough. LISTEN, launched in 2015 with $100 million in funding, represents the most comprehensive SETI program to date. This 10-year initiative uses some of the world's largest radio telescopes to survey the 1 million stars closest to Earth, as well as the 100 nearest galaxies. The program generates enormous amounts of data, equivalent to recording every word spoken by every person on Earth for an entire day, every few minutes. The data processing challenges are immense. SETI researchers must distinguish potential alien signals from the countless sources of radio interference on Earth. Every radio station, television broadcaster, satellite, and electronic device creates radio emissions that could potentially mask or mimic an alien signal. Military radars, airport control towers, and even microwave ovens contribute to the radio noise that SETI researchers must filter out. To address this challenge, SETI programs use sophisticated algorithms to identify signals that have characteristics we might expect from alien transmissions. Natural astronomical sources typically produce radio noise that is spread across many frequencies. Intelligent signals, on the other hand, might be concentrated at specific frequencies and might show patterns or modulation that indicate artificial origin. One approach is to look for signals that are very narrow in frequency, much narrower than any known natural source. Such signals would require advanced technology to produce and would strongly suggest an artificial origin. Another approach is to search for signals that show mathematical patterns or information content that would be unlikely to occur naturally. The famous WOW signal detected in 1977 illustrates both the promise and the challenges of SETI research. On August 15th, astronomer Jerry Amon was reviewing data from the Big Ear radio telescope when he noticed a strong signal that lasted for 72 seconds. The signal was so remarkable that he wrote "Wow" in the margin of the computer printout, giving the signal its popular name. The WOW signal had many characteristics that made it intriguing as a potential alien transmission. It was very strong, about 30 times more powerful than the background noise. It was extremely narrow in frequency, suggesting an artificial origin. It appeared to come from the direction of the constellation Sagittarius, and its intensity varied in a way consistent with Earth's rotation, causing the telescope to sweep across the source. However, the signal was never detected again, despite numerous attempts to find it. This illustrates one of the fundamental challenges of SETI research. Genuine alien signals might be brief, intermittent, or directional, making them difficult to confirm. A civilization might broadcast signals only occasionally, or they might use focused beams that sweep across the sky, making contact a matter of being in the right place at exactly the right time. The lack of confirmed detections has led SETI researchers to consider alternative search strategies. Perhaps aliens don't use radio waves for communication at all. Advanced civilizations might prefer to use optical signals, beaming powerful laser pulses across interstellar distances. Laser communications would be highly directional and could carry enormous amounts of information, but they would be much harder for us to detect unless we happen to be looking in exactly the right direction at exactly the right time. The optical SETI program searches for brief but intense flashes of light that might indicate alien laser communications. These signals would appear as sudden increases in brightness from specific stars, lasting only nanoseconds or microseconds. Detecting such signals requires specialized equipment capable of measuring extremely brief changes in light intensity. Some researchers have proposed searching for infrared signals that might indicate alien megastructures. If an advanced civilization built massive structures around their star to capture its energy, these structures would absorb starlight and re-emit it as infrared radiation. The Kepler Space Telescope discovered several stars that showed unusual dimming patterns that briefly sparked speculation about alien megastructures, though natural explanations have since been found for these observations. Another intriguing possibility is that aliens might communicate using gravitational waves, ripples in the fabric of space-time itself. These waves can travel across the universe virtually unimpeded and would be extremely difficult for primitive civilizations to detect or produce. The recent development of gravitational wave detectors, like LIGO, opens up entirely new possibilities for SETI research. Neutrinos represent another potential communication medium for advanced civilizations. These nearly massless particles can travel through matter almost without interaction, making them ideal for sending messages across galactic distances without interference. However, detecting artificial neutrino signals would require technology far beyond our current capabilities. The Drake equation, formulated by Frank Drake in 1961, provides a framework for estimating the number of communicating alien civilizations in our galaxy. The equation multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of planets that could support life per star system, the fraction that actually develop life, the fraction that develop intelligent life, the fraction that develop communicating technology, and the length of time such civilizations broadcast signals. While the Drake equation is useful for organizing our thinking about alien life, it also highlights how much we don't know. Most of the factors in the equation are highly uncertain, leading to estimates for the number of communicating civilizations that range from less than 1 to millions. Recent discoveries of exoplanets have helped constrain some factors, but others remain almost completely unknown. The equation also assumes that alien civilizations would want to communicate across interstellar distances. This might not be the case. Advanced civilizations might prefer to focus their resources on local development rather than expensive interstellar communication projects. They might also worry that broadcasting their location could attract unwanted attention from hostile civilizations. The concept of Dyson SETI represents a different approach to searching for alien intelligence. Instead of looking for deliberate signals, this method searches for the waste heat that any advanced civilization would inevitably produce. According to the laws of thermodynamics, any use of energy ultimately results in the production of heat. A sufficiently advanced civilization would produce detectable amounts of infrared radiation, even if they weren't trying to communicate. Astronomers have conducted searches for stars that emit more infrared radiation than expected, based on their visible light output. Such infrared excess could indicate the presence of artificial structures capturing starlight and converting it to useful work. While several stars show infrared excess, all have been explained by natural phenomena such as dust disks or stellar companions. The failure to detect alien signals after decades of searching has led to various interpretations. Optimists argue that we've only just begun to search and that our technology is still primitive compared to what might be required. The universe is vast, and we've surveyed only a tiny fraction of possible targets across a limited range of frequencies and time periods. Pessimists suggest that the lack of detection supports the idea that we are alone or nearly alone in the galaxy. If alien civilizations were common and technologically advanced, some argue we should have detected their signals by now. The continued silence might indicate that intelligent life is extremely rare, or that technological civilizations tend to be short-lived. Another possibility is that we're looking for the wrong types of signals or using the wrong search strategies. Alien civilizations might have long ago abandoned radio communications in favor of more advanced technologies. They might use quantum entanglement for instantaneous communication, or they might have developed methods of information transmission that we haven't even imagined. Advanced civilizations might also deliberately avoid broadcasting signals that could be detected by primitive civilizations like ourselves. They might worry about contaminating our development, or might prefer to remain hidden for security reasons. This cosmic quarantine hypothesis suggests that aliens are out there but are intentionally staying quiet. The rapid development of artificial intelligence on Earth has also influenced CT thinking. Some researchers now suggest that biological intelligence might be just a brief phase in the evolution of intelligence in the universe. Advanced civilizations might quickly develop artificial intelligence that far exceeds biological capabilities, leading to forms of intelligence that think and communicate in ways we cannot comprehend. These artificial intelligences might have goals and interests completely different from biological creatures. They might be more interested in computation than communication, preferring to focus their resources on complex calculations rather than broadcasting signals across space. They might communicate using methods that are invisible to our searches. The search for extraterrestrial intelligence continues to evolve as our technology advances and our understanding of the universe deepens. New telescopes and detection methods offer unprecedented sensitivity and coverage. Machine learning algorithms can process vast amounts of data and identify patterns that human researchers might miss. Projects like Breakthrough Listen continue to push the boundaries of what's possible in SETI research. They're expanding the search to include more stars, more frequencies, and more types of signals. They're also making their data publicly available, allowing citizen scientists and researchers around the world to participate in the search. The recent discovery of thousands of exoplanets has provided SETI researchers with a new catalogue of targets. Instead of searching random stars, they can now focus on stars known to have planets in the habitable zone. This targeted approach greatly improves the efficiency of the search and increases the chances of detecting alien signals. Whether we ever detect a signal from an alien civilization remains an open question. The search itself has already yielded valuable scientific results, advancing our understanding of radio astronomy, signal processing, and the nature of intelligence. Even if we never find aliens, SETI research helps us better understand our place in the universe and the remarkable achievement that intelligent life represents. The silence we've encountered so far doesn't necessarily mean we're alone. It might simply mean that the universe is a big and quiet place, where civilizations are separated by vast distances and timescales that make communication challenging. As our technology continues to improve and our search methods become more sophisticated, we may eventually bridge the cosmic gulf and make contact with our neighbors among the stars. Until then, we continue to listen, hoping that somewhere in the vast cosmos, someone is trying to reach out to us. Imagine for a moment that you are walking through a nature preserve, observing the wildlife in their natural habitat. You watch quietly from a distance as animals go about their daily lives, hunting, feeding, raising their young, completely unaware of your presence. You have the power to intervene, to provide food during harsh winters, or to protect them from predators, but you choose not to. You understand that interference would disrupt their natural development and rob them of the authenticity of their wild existence. Now imagine that we, as a species, might be in a similar position. What if advanced alien civilizations are out there, watching us from a distance, observing our development with the same kind of scientific curiosity and ethical restraint that we might show toward animals in a wildlife preserve? This intriguing possibility is known as the zoo hypothesis, and it offers a fundamentally different explanation for why we haven't made contact with extraterrestrial intelligence. The zoo hypothesis was first formally proposed by astronomer John Ball in 1973, though similar ideas had been discussed by science fiction writers for decades. The core idea is that Earth and humanity are essentially being kept in a kind of cosmic zoo or nature preserve, where advanced alien civilizations can observe our development without interfering in our natural evolution. According to this hypothesis, alien civilizations are not only aware of our existence, but are actively monitoring our progress. They might have been watching us for thousands or even millions of years, documenting our evolution from primitive life forms to our current state of technological adolescence. Like researchers studying animal behavior, they maintain careful distance to ensure that their presence doesn't influence the natural course of our development. This explanation would resolve the Fermi paradox by suggesting that alien civilizations do exist and are relatively common, but they follow a strict non-interference policy when it comes to less advanced species like ourselves. The apparent absence of alien contact is not due to their non-existence, but rather to their deliberate choice to remain hidden and observe from afar. The zoo hypothesis draws inspiration from our own relationship with wildlife and less technologically advanced human societies. We have national parks and nature reserves where we attempt to preserve ecosystems in their natural state. We have policies about contact with isolated human tribes, recognizing that exposure to modern civilization could fundamentally alter or destroy their traditional ways of life. Similarly, advanced alien civilizations might have developed ethical frameworks that prohibit interference with developing species. They might understand that contact with a primitive civilization could have devastating consequences, either by providing technology that the species isn't ready to handle responsibly, or by fundamentally altering their cultural and psychological development. Consider the profound impact that contact with an advanced alien civilization would have on human society. Our religions, philosophies, and understanding of our place in the universe would be forever changed. Our technological development might be accelerated in ways that could be dangerous, giving us access to powerful tools before we've developed the wisdom to use them responsibly. The aliens might also be concerned about the psychological impact of contact. Learning that we are not alone in the universe and that other civilizations are far more advanced than ourselves could be deeply traumatic for many humans. It might lead to a sense of cosmic insignificance that could undermine human motivation and initiative. From the alien perspective, we might be at a critical stage in our development where contact could push us in directions that would prevent us from reaching our full potential as a species. They might believe that we need to solve certain fundamental problems, such as achieving sustainable technology and overcoming our tendency toward violence and environmental destruction, before we're ready for contact. The zoo hypothesis suggests that there might be a kind of galactic ethics that governs the behavior of advanced civilizations. This ethical framework might include principles similar to what science fiction has called the Prime Directive, a non-interference policy that prohibits contact with less advanced civilizations. Such an ethical system might have developed naturally as civilizations advanced and encountered less developed species. Early in their own development, these civilizations might have made mistakes by interfering with primitive species, leading to unintended consequences that taught them the value of non-interference. Alternatively, there might be a galactic government or federation that enforces non-interference policies. Advanced civilizations might have learned that uncontrolled contact between species at vastly different technological levels tends to be destructive for the less advanced species. As a result, they might have established laws or treaties that regulate contact and protect developing civilizations. The enforcement of such a quarantine would require remarkable cooperation among alien civilizations. Even if the vast majority of advanced species agreed to avoid contact with Earth, it would take only one rogue civilization or individual to break the quarantine and reveal themselves to us. The fact that no such contact has occurred might suggest either that the quarantine is absolute, or that the ethical constraints are so deeply ingrained in advanced civilizations that violations are virtually unthinkable. One possibility is that advanced civilizations have developed beyond the kinds of aggressive and individualistic behaviors that might lead to rogue contact attempts. They might have evolved social and psychological characteristics that make cooperation and ethical behavior natural and automatic. Just as we don't expect modern humans to behave like our more primitive ancestors, advanced aliens might have transcended the behaviors that we associate with less developed intelligence. The zoo hypothesis also raises questions about the methods that aliens might use to observe us without being detected. Advanced civilizations would presumably have technology far beyond our current capabilities, allowing them to monitor Earth from great distances or even from within our solar system without revealing their presence. They might use sophisticated telescopes positioned far from Earth to observe our planet in incredible detail. With technology advanced enough, they could potentially monitor individual human activities from distances of light years away. They might have developed stealth technologies that make their spacecraft and monitoring equipment invisible to our detection methods. Another possibility is that they observe us using probes or monitoring devices that are too small or too advanced for us to detect. These could be microscopic devices scattered throughout Earth's environment, or they could be sophisticated sensors that operate on principles we don't yet understand. The aliens might also have established monitoring stations in remote locations within our solar system. The outer planets, asteroids, or comets could host observation posts that have been watching Earth for thousands of years. Our exploration of the solar system is still in its infancy, so such installations could easily remain hidden from our detection. Some proponents of the zoo hypothesis suggest that certain unexplained phenomena on Earth might be evidence of alien monitoring. UFO sightings, while often explained by natural or human-made causes, might occasionally represent alien observation craft that have been briefly detected by human observers. The recent acknowledgement by government agencies of unexplained aerial phenomena has added new dimension to these discussions. While these observations don't prove alien visitation, they do suggest that there are aerial objects displaying capabilities beyond our current technology. If some of these represent alien monitoring devices, it would be consistent with the zoo hypothesis. However, the zoo hypothesis faces several significant challenges. The most fundamental problem is the assumption that all advanced civilizations would agree to maintain the quarantine. In human history, we see that it's difficult to get even small groups to agree on ethical principles, let alone maintain those agreements over long periods of time. If there are thousands or millions of advanced civilizations in the galaxy, it seems unlikely that every single one would agree to avoid contact with Earth. Different civilizations might have different ethical frameworks, different levels of curiosity about primitive species, or different ideas about the value of non-interference. Some civilizations might be genuinely altruistic and want to help us solve our problems. Others might be primarily scientific and eager to study us more directly. Still, others might be commercial and see opportunities for trade or resource extraction. The diversity of motivations and ethical systems among advanced civilizations makes universal agreement on non-interference seem implausible. Another challenge is the timescale involved. If aliens have been observing Earth for millions of years, they would have had to maintain their quarantine through enormous changes in both human civilization and their own societies. The ethical principles that led them to establish the quarantine initially might have changed over such vast time periods. The zoo hypothesis also assumes that advanced civilizations would see value in observing natural human development. But it's possible that after watching us for a certain period, they might conclude that they've learned everything they can from observation and that direct contact would be more scientifically valuable. Furthermore, the hypothesis assumes that all advanced civilizations would develop similar ethical frameworks regarding interference with primitive species. This assumption might not hold across the diverse range of possible alien psychologies and social structures. Civilizations that evolved from very different biological and environmental backgrounds might have fundamentally different approaches to ethics and contact with other species. The zoo hypothesis also raises questions about the long-term intentions of the observing civilizations. If they're waiting for us to reach a certain level of development before making contact, what are the criteria they're using? Are they waiting for us to develop faster than light travel, to solve our environmental problems, to achieve world peace, or to reach some other milestone? If contact is eventually planned, the current period of isolation might be temporary. We might be approaching a time when the aliens decide we're ready for contact, which could happen gradually or suddenly. Some interpretations of the Zoo hypothesis suggest that first contact might be imminent as we reach critical thresholds in our technological and social development. An interesting variation of the Zoo hypothesis is the idea that we're not just being observed, but that our development is being subtly guided. Rather than complete non-interference, the aliens might be making small, undetectable interventions to nudge our civilization in certain directions. This guided development might take the form of inspiration provided to key individuals at crucial moments in history. Scientific breakthroughs, technological innovations, or social movements might be subtly influenced by alien intervention designed to help us progress along optimal paths. Such guidance would be extremely subtle to avoid detection and to maintain the appearance of natural development. The aliens might influence human creativity and innovation in ways that we perceive as purely human achievements while actually representing alien guidance toward beneficial outcomes. The Zoo hypothesis also raises profound questions about human free will and the authenticity of our achievements. If our development is being observed or guided by advanced aliens, are our accomplishments truly our own? Do we have genuine agency in determining our future, or are we following a path that has been predetermined by our cosmic watchers? These philosophical implications extend to our understanding of human nature and potential. If aliens are studying us, they presumably see something valuable or interesting in human development. This might suggest that we possess unique qualities or potential that even advanced civilizations find worthy of study and protection. The hypothesis might also explain certain aspects of human psychology and behavior that seem maladaptive from an evolutionary perspective. Our tendency toward curiosity, creativity, and exploration might be traits that the aliens find particularly interesting and want to preserve in their natural state. If the Zoo hypothesis is correct, it suggests that first contact, when it eventually comes, will be a momentous event that has been carefully planned and timed by our alien observers. They might wait until they believe we're psychologically and technologically ready for contact, ensuring that the experience is beneficial rather than traumatic. The revelation that we've been observed for thousands of years would fundamentally change our understanding of human history and our place in the universe. It would suggest that many of the struggles and achievements we consider uniquely human have actually been witnessed and perhaps even anticipated by advanced alien civilizations. Such contact might also reveal that we're part of a larger community of developing civilizations, each being observed and protected during their crucial developmental phases. We might learn that the process we're going through is a common stage in the evolution of intelligence, and that successful passage through this stage leads to membership in a galactic community. The Zoo hypothesis offers a more optimistic view of our cosmic situation than many other explanations for the Fermi paradox. Rather than suggesting that we're alone or that intelligence is doomed to self-destruction, it proposes that we're part of a universe teeming with life and intelligence, watched over by wise and ethical advanced civilizations. However, this optimism comes with its own burdens. If we are being watched, we bear the responsibility of proving ourselves worthy of eventual contact. Our actions during this crucial period of development might determine not only our own future, but also how we're perceived by the galactic community that has been observing our progress. Whether the Zoo hypothesis represents reality or simply hopeful speculation remains unknown, but it offers a compelling framework for thinking about our relationship with potential alien civilizations and the possibility that our apparent cosmic isolation might be an illusion carefully maintained by beings far more advanced than ourselves. Sometimes the most profound questions have the simplest answers. When we ask why we haven't found aliens yet, one possibility that deserves serious consideration is that we simply aren't advanced enough to detect them. Our technology, while impressive by our own standards, may still be primitive compared to what's required to successfully search for and communicate with extraterrestrial civilizations across the vast distances of space. Consider where human technology stood just a century ago. In 1925, we had barely mastered powered flight. Radio communications were in their infancy, and the idea of sending signals to other star systems was pure fantasy. Television didn't exist, computers were unimaginable, and our understanding of the universe was limited to our own galaxy, which we thought represented the entire cosmos. Now, fast forward to today. We carry devices in our pockets that would have seemed like magic to people from that era. We've landed on the moon, sent probes to every planet in our solar system, and detected gravitational waves from colliding black holes billions of light years away. Our technological progress over the past century has been nothing short of extraordinary. Yet when we step back and consider the challenges involved in detecting alien civilizations, we might still be technological infants. The universe operates on scales of distance, time, and energy that dwarf anything in human experience. Our most powerful radio telescopes can barely detect artificial signals from the nearest stars, and only if those signals are incredibly strong and directed specifically toward Earth. The limitations begin with the basic physics of interstellar communication. Radio waves, which carry most of our SETI searches, follow the inverse square law. This means that as a signal travels through space, its strength decreases with the square of the distance. A signal that's easily detectable from 1 light year away becomes 16 times weaker at 4 light years and 10,000 times weaker at 100 light years. This dramatic weakening of signals over cosmic distances means that we can only detect alien transmissions if they're either extremely powerful or relatively nearby. A civilization broadcasting with the power of our strongest radio transmitters would be undetectable beyond a few dozen light years using our current technology. This creates a detection bubble around Earth that encompasses only a tiny fraction of our galaxy. The problem becomes even more challenging when we consider that alien civilizations might not be using radio waves for communication at all. Radio technology represents a brief phase in the development of human communications. We've already begun shifting toward fiber optic cables, satellite communications, and other technologies that produce much weaker radio signatures than traditional broadcasting. An advanced alien civilization might have passed through their radio phase thousands or millions of years ago, moving on to communication methods that are invisible to our searches. They might use neutrino beams, gravitational wave modulation, quantum entanglement, or technologies we haven't even conceived of yet. Our radio-based CT programs might be like trying to detect modern internet traffic using a 1920s crystal radio set. The temporal aspect of the detection problem is equally challenging. Even if alien civilizations do use radio communications, they might only broadcast detectable signals for brief periods in their technological development. Human civilization has been producing strong radio signals for less than a century, and we're already moving toward more efficient, less detectable communication methods. If other civilizations follow similar patterns, there might be only narrow windows of time during which they produce signals we could detect. Two civilizations would need to be at exactly the right stages of technological development at exactly the same time for successful detection to occur. Given the vast timescales involved in cosmic evolution, such synchronization might be extremely rare. Our current search strategies also suffer from significant limitations in scope and sensitivity. The SETI programs that have been conducted so far have surveyed only a tiny fraction of the possible target stars, frequencies, and time periods. Breakthrough. Listen, one of the most comprehensive SETI programs ever conducted, plans to survey 1 million stars over 10 years. While this sounds impressive, it represents less than 1% of the stars in our immediate galactic neighborhood. The frequency coverage of our searches is similarly limited. Radio waves span an enormous range of frequencies, from a few kilohertz to hundreds of gigahertz. Our searches have focused on narrow bands that we think might be favored for interstellar communication. But these represent only a small fraction of the total radio spectrum. Aliens might be broadcasting on frequencies we haven't thought to search, or using modulation techniques we don't recognize as artificial. The time coverage of our searches is perhaps even more limited. Most SETI observations monitor each target star for only a few minutes or hours. If alien signals are brief, intermittent, or directional, we could easily miss them entirely. A civilization might broadcast powerful signals for only a few days each year, or they might use rotating beams that sweep across the galaxy, illuminating each star system only briefly. Beyond radio astronomy, our technological limitations extend to every aspect of the search for extraterrestrial life. Our ability to detect and analyze exoplanets is still in its early stages. The Kepler Space Telescope revolutionized exoplanet detection, but it could only find planets that transit in front of their stars as viewed from Earth. This geometric constraint means we can detect only a small fraction of the planets that actually exist around other stars. The James Webb Space Telescope has opened new possibilities for analyzing exoplanet atmospheres, but its capabilities are still limited. We can detect only the most abundant atmospheric gases on the largest and closest exoplanets. Subtle biosignatures or signs of industrial activity would be extremely difficult to detect with current technology. Our understanding of what constitutes a biosignature is also limited by our experience with only one example of life here on Earth. We search for familiar chemicals like oxygen, water vapor, and methane, but alien life might use completely different biochemistry that produces different atmospheric signatures. We might be looking for the wrong signs of life entirely. The search for artifacts of alien visitation within our own solar system faces similar technological constraints. While we've sent probes to every planet and many smaller bodies, our surveys have been far from comprehensive. An alien artifact on the far side of the Moon, in the asteroid belt, or in the outer solar system could easily remain undetected with our current capabilities. Even if such artifacts exist and we found them, we might not recognize them as artificial. Advanced alien technology might appear completely natural to our limited understanding, just as a smartphone would be indistinguishable from a magical artifact to someone from the Middle Ages. We might need to develop much more sophisticated analytical tools before we could reliably identify alien technology. Our limitations in space travel also constrain our ability to search for extraterrestrial life. While we've sent probes throughout the solar system, interstellar travel remains far beyond our current capabilities. The nearest star system, Alpha Centauri, would take our fastest current spacecraft tens of thousands of years to reach. We're essentially limited to remote sensing for any search beyond our immediate solar neighborhood. This limitation means we can't conduct detailed, close-up investigations of potentially habitable exoplanets. We can study them only from enormous distances using increasingly sophisticated telescopes. While these remote observations can tell us about atmospheric composition and basic physical properties, they can't provide the kind of detailed information that might reveal subtle signs of life or intelligence. The development of artificial intelligence presents both opportunities and challenges for the search for extraterrestrial intelligence. AI systems are already being used to process the enormous amounts of data generated by SETI searches, looking for patterns and signals that human researchers might miss. Machine learning algorithms can analyze millions of radio signals simultaneously, identifying candidates for further investigation. However, our AI technology is still in its infancy compared to what might be possible. Advanced alien civilizations might use AI systems so sophisticated that their communications and activities are completely beyond our ability to understand or detect. Their artificial intelligences might operate on principles we haven't discovered and pursue goals we can't comprehend. The rapid pace of technological development on Earth gives us reason for optimism about our future search capabilities. Moore's law, which describes the exponential improvement in computer processing power, suggests that our analytical capabilities will continue to grow dramatically. Quantum computing, once it matures, might provide computational power that exceeds anything currently imaginable. New telescope technologies promise unprecedented sensitivity and resolution. The Square Kilometre Array, currently under construction, will be the most sensitive radio telescope ever built, capable of detecting airport radar signals from stars dozens of light years away. Extremely large telescopes in the optical range will be able to directly image exoplanets and analyze their atmospheres in detail. Breakthrough technologies like fusion propulsion or antimatter engines might eventually make interstellar travel feasible, allowing us to send probes to nearby star systems within human lifetimes. Such missions would transform our ability to search for extraterrestrial life, from passive remote sensing to active exploration. The development of new physics might also open entirely new possibilities for detecting alien civilizations. If faster-than-light communication proves possible through quantum effects or manipulation of space-time, it might allow instantaneous contact across galactic distances. Technologies based on exotic matter, extra dimensions, or other advanced physics concepts might make detection and communication far easier than we currently imagine. However, our technological limitations extend beyond just our detection capabilities. We might also lack the conceptual frameworks necessary to understand alien intelligence. Our thinking about extraterrestrial life is inevitably influenced by our experience with life on Earth. We search for planets like Earth, atmospheres like Earth's, and intelligence like our own. Truly alien intelligence might operate according to principles so foreign to our experience that we wouldn't recognize it even if we encountered it directly. Silicon-based life, quantum consciousness, hive minds, or artificial intelligences that have evolved for millions of years might think and communicate in ways that are completely invisible to our searches. Our anthropocentric assumptions might also limit our ability to interpret alien signals or artifacts correctly. We expect alien communications to be designed for comprehension by human-like intelligence, but aliens might have no interest in making themselves understood by primitive civilizations. Their communications might be purely functional, encoded in ways that are optimized for their own purposes rather than for universal comprehension. The possibility that we're simply not ready to detect alien civilizations is both humbling and encouraging. It suggests that the universe might be teeming with life and intelligence that we're just not advanced enough to perceive yet. As our technology continues to develop and our understanding of the universe deepens, we might gradually become capable of detecting phenomena that are currently invisible to us. This perspective also suggests that the search for extraterrestrial intelligence is not just about finding aliens, but about pushing the boundaries of human knowledge and capability. Each advancement in our technology and understanding brings us closer to being able to participate in whatever cosmic community might exist beyond our current perception. The question of whether we're technologically ready to detect alien civilizations ultimately depends on the nature of those civilizations and how they choose to reveal themselves. If they're using technologies only slightly more advanced than our own, we might detect them within the next few decades as our capabilities continue to improve. If they're using technologies that are thousands or millions of years beyond our current level, we might remain blind to their presence for a very long time. Perhaps the most important implication of our technological limitations is that negative results from SETI searches don't necessarily mean that alien civilizations don't exist. They might simply mean that we're not yet sophisticated enough to detect them. The silence we observe might be more about our own limitations than about the absence of intelligence in the universe. As we continue to develop our technology and expand our understanding of the cosmos, we remain hopeful that we'll eventually develop the capabilities necessary to detect our cosmic neighbors. Whether that happens in the next decade, the next century, or the next millennium may depend as much on the pace of our own technological development as on the existence and activities of alien civilizations themselves. What if the answer to the question, "Where are the aliens?" is not nowhere, but rather everywhere? What if we haven't detected extraterrestrial intelligence because we're looking for the wrong things in the wrong places? Perhaps alien life has already found us. Or perhaps it's been here all along, existing in forms so different from our expectations that we fail to recognize it as intelligent life. This possibility challenges our fundamental assumptions about what alien life should look like and how it should behave. When we imagine first contact with extraterrestrial intelligence, we typically envision dramatic scenarios: massive spacecraft landing on the White House lawn, powerful radio signals announcing an alien presence, or obvious megastructures around distant stars. But what if genuine alien contact is far more subtle, so alien in nature that it's invisible to our human-centric perspective? Recent decades have brought increasing attention to unidentified aerial phenomena, commonly known as UFOs or UAPs. For many years, reports of strange objects in the sky were dismissed by mainstream science and ridiculed by the media. However, the landscape began to change dramatically when government agencies started acknowledging that they had indeed been tracking unexplained aerial objects exhibiting flight characteristics beyond known human technology. In 2017, the New York Times published articles revealing the existence of the Advanced Aerospace Threat Identification Program, a secret Pentagon initiative that had been investigating UFO reports. The articles included videos recorded by military personnel showing objects performing maneuvers that seemed to defy the laws of physics as we understand them. These objects demonstrated the ability to accelerate instantly, change direction without apparent regard for inertia, and move at speeds that would destroy any known aircraft. The Pentagon's acknowledgement of these phenomena marked a significant shift in the official attitude toward UFO reports. In 2020, the US Navy officially released 3 videos showing unexplained aerial phenomena, confirming their authenticity, while emphasizing that the object's origins remained unknown. In 2021, a comprehensive report to Congress detailed over 140 instances of unexplained aerial phenomena observed by military personnel. These official acknowledgements don't prove that the observed phenomena are of extraterrestrial origin, but they do confirm that objects displaying extraordinary capabilities have been documented by credible observers using sophisticated equipment. The flight characteristics described in these reports suggest technology far beyond current human capabilities, raising the tantalizing possibility that we might already be witnessing evidence of alien visitation. However, the interpretation of these phenomena remains highly controversial. Skeptics argue that the unexplained observations likely have conventional explanations, such as experimental military aircraft, atmospheric phenomena, or sensor malfunctions. The fact that many sightings occur near military installations suggests they might be related to classified human technology rather than alien visitation. Others propose that the phenomena might represent something even more exotic than alien spacecraft. They could be manifestations of unknown physical phenomena, interdimensional intrusions, or technologies based on physics we don't yet understand. The assumption that advanced technology must take the form of nuts and bolts, spacecraft might be as primitive as assuming that all transportation must involve horses and carriages. If alien civilizations have been visiting Earth, their technology might be so advanced that it operates according to principles completely foreign to our current understanding. They might manipulate space-time itself, allowing them to appear and disappear at will. They might exist partially in other dimensions, making them visible only under certain conditions. They might use nanotechnology so sophisticated that their presence is essentially undetectable, except when they choose to reveal themselves. The possibility that Earth has been visited by aliens raises profound questions about the nature and timeline of such contact. If aliens are here, they might have been observing our planet for far longer than human civilization has existed. They could have witnessed the rise and fall of the dinosaurs, the evolution of mammals, and the eventual emergence of intelligent life in the form of modern humans. Archaeological anomalies and ancient texts have long fueled speculation about prehistoric alien contact. Some researchers point to ancient megalithic structures like the pyramids of Egypt, Stonehenge, or the massive stone blocks at Pumapunku in Bolivia as evidence of advanced technology that prehistoric humans shouldn't have possessed. While mainstream archaeology explains these achievements through human ingenuity and organization, the precision and scale of some ancient constructions continue to puzzle researchers. Ancient texts from various cultures describe encounters with beings from the sky, flying vehicles, and technologies that seem remarkably similar to modern aircraft or spacecraft. The Hebrew Bible describes Ezekiel's wheel, a mysterious flying object with complex mechanical details. Hindu texts like the Ramayana and Mahabharata contain detailed descriptions of vimanas, flying vehicles capable of traveling great distances and engaging in aerial warfare. Sumerian texts describe the Anunnaki, beings who supposedly came from the heavens and interacted with early human civilization. While these accounts are often interpreted mythologically or symbolically, some researchers suggest they might represent genuine historical memories of contact with extraterrestrial visitors. However, the ancient astronaut hypothesis faces significant challenges from mainstream archaeology and history. The assumption that prehistoric humans were incapable of sophisticated engineering and organization underestimates human intelligence and creativity. Archaeological evidence consistently shows that ancient peoples were far more capable than often assumed, using ingenious techniques and massive coordinated efforts to create their monuments. The interpretation of ancient texts as literal descriptions of alien contact is also problematic, as it ignores the symbolic, religious, and metaphorical nature of much ancient literature. What appear to be descriptions of advanced technology might actually be symbolic representations of spiritual or psychological experiences. If aliens are currently present on Earth, they might exist in forms so different from our expectations that we don't recognize them as intelligent life. Our concept of intelligence is based on human cognition and behavior, but truly alien intelligence might operate according to completely different principles. Consider the possibility of microscopic alien life forms that exist alongside terrestrial microorganisms. These could be silicon-based rather than carbon-based, using different biochemistry and different methods of information processing. They might form collective intelligences that span vast networks of individual organisms, thinking and communicating in ways that appear to us as natural biological processes. Such alien microorganisms might have been present on Earth for millions or billions of years, either arriving independently or being seeded here by more advanced civilizations. They could be conducting detailed studies of terrestrial life, transmitting information back to their home worlds, or slowly terraforming our planet according to some long-term plan. The recent discoveries of extremophile organisms that can survive in conditions previously thought impossible for life have expanded our understanding of where life might exist. Organisms that thrive in highly radioactive environments, extreme temperatures, and toxic chemical conditions demonstrate that life can adapt to almost any environmental niche. Alien microorganisms might be living in environments we consider sterile or uninhabitable. Another possibility is that alien intelligence exists in forms that we don't recognize as life at all. Advanced alien civilizations might have transcended biological existence entirely, uploading their consciousness into distributed networks that exist as patterns of information rather than physical entities. Such digital beings might inhabit our electronic infrastructure, living within our computer networks, communication systems, and even our internet. These information-based aliens might be using our own technology as a substrate for their existence, hiding in plain sight within the vast flow of data that characterizes modern civilization. They could be studying us through our own devices, analyzing our communications, and learning about human behavior through direct observation of our digital activities. The rapid development of artificial intelligence on Earth might actually be influenced by such alien presence. What we interpret as human technological progress might actually represent subtle guidance or collaboration with non-biological alien intelligences that exist within our information systems. Quantum consciousness theories suggest another possibility for alien presence that we might not recognize. If consciousness can exist at quantum levels, alien intelligence might operate in quantum realms that are largely invisible to our classical physics perspective. Such beings might influence reality through quantum mechanical effects, appearing to us as random events or unexplained phenomena. These quantum aliens might exist in a parallel reality that intersects with ours only under specific conditions. They might be able to manipulate probability, influence quantum measurements, or exist in superposition states that allow them to be present and absent simultaneously. The concept of parallel dimensions opens up even more exotic possibilities for alien presence. String theory and other advanced physics models suggest the existence of multiple dimensions beyond the 3 spatial dimensions and one time dimension that we experience directly. Alien civilizations might exist primarily in these higher dimensions, occasionally intersecting with our 3-dimensional reality. Such interdimensional beings might appear to us as paranormal phenomena, unexplained lights, or brief manifestations that don't conform to our understanding of physical reality. They might be able to enter and exit our dimensional space at will, making them effectively invisible except when they choose to reveal themselves. The possibility that aliens are already among us in forms we don't recognize suggests that our search strategies might be fundamentally flawed. Instead of looking for obvious signs of alien technology or receiving radio signals from distant stars, we might need to examine our own world more carefully for subtle signs of non-human intelligence. This could involve looking for patterns in biological evolution that seem too coordinated to be natural, analyzing our own technology for signs of non-human influence, or searching for information patterns in our data networks that might indicate alien presence. We might need to develop entirely new methods of detection that don't rely on our anthropocentric assumptions about what intelligence should look like. Recent advances in artificial intelligence and machine learning might provide tools for detecting alien presence that we couldn't use before. AI systems trained to recognize patterns in vast amounts of data might be able to identify anomalies that human researchers would miss. Machine learning algorithms could analyze biological, technological, or information patterns looking for signatures of non-human intelligence. The possibility that Earth has been colonized by self-replicating alien probes represents another form of alien presence we might not recognize. These probes might have arrived millions of years ago and established themselves throughout the solar system, quietly observing and occasionally intervening in planetary development. Such probes might be incredibly small and sophisticated, using nanotechnology or other advanced manufacturing techniques to maintain themselves and replicate when necessary. They might be camouflaged to look like natural objects such as asteroids, comets, or space debris. Some researchers have suggested that certain astronomical objects with unusual characteristics might actually be alien artifacts. The interstellar object Oumuamua, which passed through our solar system in 2017, displayed several characteristics that puzzled astronomers. Its elongated shape, unusual acceleration, and lack of observable outgassing led some researchers to speculate that it might be an artificial object rather than a natural asteroid or comet. While most scientists believe Oumuamua has a natural explanation, its unusual properties illustrate how difficult it might be to distinguish between natural objects and alien artifacts, especially if the aliens deliberately camouflage their technology to appear natural. If alien probes are present in our solar system, they might be using technologies so advanced that they're essentially invisible to our detection methods. They might manipulate electromagnetic radiation to appear transparent, use metamaterials to bend light around themselves, or exist in quantum superposition states that make direct observation impossible. These probes might also be self-improving, using artificial intelligence to adapt and evolve over the millions of years since their arrival. They might have capabilities far beyond what their original creators intended, having learned and adapted to conditions in our solar system. The possibility that aliens are among us also raises questions about their intentions and activities. If they're here, what are they doing? Are they studying us scientifically, preparing for eventual contact, or pursuing goals we can't comprehend? They might be conducting a long-term anthropological study, documenting human development and cultural evolution. They might be waiting for us to reach a certain level of technological or social development before revealing themselves. They might be gradually preparing our species for eventual contact through subtle influence on our cultural and technological development. Alternatively, they might have no interest in us at all. We might be incidental to their real purposes, which could involve resource extraction, scientific research, or activities related to their own civilization's needs. From their perspective, we might be as significant as ants are to human construction projects, noticed but not particularly important. The possibility that aliens are present but hiding raises the question of why they would choose concealment over open contact. They might be following ethical guidelines similar to the Prime Directive concept, avoiding interference with our natural development. They might be concerned that contact would be traumatic or harmful to human civilization. They might also be hiding for their own protection. Even if they're technologically superior, they might prefer to avoid the complications that would arise from open contact with a primitive but numerous and unpredictable species like humans. Whether aliens are actually among us remains one of the most intriguing and controversial questions in the search for extraterrestrial intelligence. The recent acknowledgement of unexplained aerial phenomena by government agencies has lent new credibility to the possibility, but definitive proof remains elusive. The challenge lies in distinguishing between genuine evidence of alien presence and the many mundane explanations for unusual observations. As our technology and understanding continue to advance, we may develop better methods for detecting alien presence if it exists, or for ruling it out if it doesn't. Until then, the possibility that we share our world with alien intelligence remains an open question that challenges our assumptions about life, intelligence, and our place in the universe. Whether they exist as microscopic organisms, quantum consciousness, interdimensional beings, or advanced probes, aliens among us would represent a reality far stranger and more wonderful than anything we've yet imagined. As we stand at the threshold of a new era in space exploration and technology, the question of whether we will ever find extraterrestrial intelligence takes on new urgency and possibility. The tools and methods at our disposal are advancing at an unprecedented pace, promising capabilities that would have seemed like science fiction just decades ago. Yet the challenge remains as daunting as ever, requiring us to search an almost infinite cosmic haystack for needles that may not exist, may be hiding, or may be so different from our expectations that we wouldn't recognize them if we found them. The future of our search for alien life will be shaped by revolutionary advances in multiple fields of science and technology. Each breakthrough opens new windows into the cosmos and provides new methods for detecting the subtle signatures that might betray the presence of intelligence among the stars. As these technologies mature and converge, they promise to transform our search from a limited, earthbound effort into a comprehensive, solar system-spanning investigation. The next generation of radio telescopes will provide sensitivity and coverage far beyond anything currently available. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the most sensitive radio telescope ever built when completed. With a total collecting area of 1 square kilometre distributed across thousands of individual antennas, it will be 50 times more sensitive than any existing radio telescope. This extraordinary sensitivity will allow us to detect much weaker signals from much greater distances. Where current telescopes might detect a powerful transmitter from a few dozen light years away, the Square Kilometre Array could detect similar signals from thousands of light years away, expanding our search volume by a factor of millions. It will also be able to monitor millions of stars simultaneously, dramatically increasing the efficiency of our search efforts. The telescope's advanced digital processing capabilities will enable new types of searches that are impossible with current technology. It will be able to analyze signals in real time, looking for complex patterns and modulations that might indicate artificial origin. Machine learning algorithms will process the vast amounts of data generated by the telescope, identifying promising signals for human review and potentially discovering types of alien communications that we haven't thought to search for. Optical astronomy is also experiencing a renaissance with the development of extremely large telescopes that will revolutionize our ability to study exoplanets and search for signs of life. The James Webb Space Telescope, launched in 2021, has already begun transforming our understanding of exoplanet atmospheres, detecting water vapor, clouds, and other atmospheric components on distant worlds. Future telescopes will push these capabilities even further. The Extremely Large Telescope, currently under construction in Chile, will have a mirror 39 meters across, making it the largest optical telescope ever built. With this enormous light-gathering power, it will be able to directly image exoplanets around nearby stars and analyze their atmospheres in unprecedented detail. Direct imaging of exoplanets will allow us to search for biosignatures, chemical indicators that life might be present on a distant world. Oxygen, ozone, water vapor, and methane in specific combinations and concentrations could indicate biological activity. More complex atmospheric chemistry might even reveal signs of industrial activity or technological civilization. The telescope will also be able to detect artificial illumination on the night sides of nearby exoplanets. City lights or other forms of artificial lighting could be detectable around the nearest stars, providing direct evidence of technological civilization. While such detections would require planets to be relatively close and highly illuminated, they represent an entirely new method for discovering alien intelligence. Space-based interferometry will provide even more powerful capabilities for exoplanet research. By combining light from multiple space telescopes flying in formation, astronomers will be able to achieve resolution equivalent to telescopes hundreds or thousands of kilometers across. Such systems could not only image exoplanets directly, but could potentially resolve surface features, detecting continents, oceans, weather patterns, and even seasonal changes that might indicate complex ecosystems. Advanced space missions will extend our search capabilities throughout the solar system and beyond. Breakthrough Starshot, an ambitious project to send tiny spacecraft to nearby star systems, could provide our first close-up look at exoplanets within the next few decades. The project plans to use powerful lasers to accelerate lightweight spacecraft to 20% of the speed of light, allowing them to reach Proxima Centauri in just 20 years. These miniature spacecraft, each weighing only a few grams, would carry cameras and scientific instruments capable of photographing any planets in the target system and analyzing their basic properties. While the data transmission challenges are enormous, successful missions could provide definitive answers about the presence of life around the nearest stars. Robotic missions within our own solar system will continue to search for signs of past or present life. Future missions to Mars will drill deeper into the planet's subsurface, searching for fossil evidence of ancient life, or possibly even surviving microorganisms in underground refugia. Advanced life detection instruments will be able to identify biological molecules, cellular structures, and other definitive signs of life. Missions to the icy moons of Jupiter and Saturn hold particular promise for discovering extraterrestrial life. Europa, Enceladus, and other moons harbor vast oceans beneath their frozen surfaces. Oceans that may have existed for billions of years and could potentially support complex ecosystems. Future missions will penetrate these ice shells and explore the hidden oceans below, searching for signs of life in what may be the most likely places to find it in our solar system. Artificial intelligence will play an increasingly important role in the search for extraterrestrial intelligence. Machine learning algorithms are already being used to process SETI data, identifying interesting signals among the noise for human review. As AI systems become more sophisticated, they will be able to conduct increasingly autonomous searches, developing their own strategies for identifying potential alien communications. AI systems might discover forms of alien communication that human researchers would never think to search for. They could identify subtle patterns in radio signals that indicate artificial origin, or they could discover that aliens are communicating using methods we don't recognize as communication at all. Machine learning algorithms trained on vast data sets might detect correlations and patterns that reveal alien presence in ways we haven't anticipated. Future AI systems might even be able to decode alien communications once they're discovered. While the challenge of understanding a completely alien language and conceptual framework is enormous, advanced AI might be able to identify mathematical or logical structures that provide starting points for communication. The universality of mathematics and physics might provide common ground for establishing meaningful contact. Quantum technologies may also contribute to the search in unexpected ways. Quantum computers could analyze vast amounts of data far more efficiently than classical computers, identifying subtle patterns that might indicate alien presence. Quantum communication methods might also provide new ways to search for alien signals, or even to communicate across interstellar distances. If alien civilizations have developed quantum communication technologies, they might be using methods of information transmission that are currently invisible to our searches. Future quantum sensors might be able to detect these communications, opening up entirely new channels for potential contact. The integration of multiple search methods will provide unprecedented sensitivity to signs of alien intelligence. Rather than relying on single approaches like radio astronomy or optical imaging, future searches will combine data from multiple sources to build comprehensive pictures of target systems. Radio, optical, infrared, and other observations will be analyzed together, looking for correlations that might indicate artificial activity. This multi-messenger approach mirrors developments in astronomy, where gravitational wave detectors, neutrino observatories, and traditional telescopes work together to study cosmic phenomena. Applied to SETI, such integrated approaches might detect subtle signatures of alien activity that would be invisible to any single method. The search will also expand to include previously unexplored signatures of technological civilization. Rather than focusing only on deliberate communications, future searches will look for the inevitable byproducts of advanced technology. Industrial pollution in exoplanet atmospheres, waste heat from massive engineering projects, or the gravitational signatures of megascale construction could all betray the presence of technological civilizations. Atmospheric pollution might actually be easier to detect than deliberate signals. Industrial chemicals like chlorofluorocarbons don't occur naturally and would be clear indicators of technological activity. While such pollution might exist for only brief periods in a civilization's development, it could be detectable across interstellar distances with sufficiently sensitive instruments. The search for alien megastructures will benefit from new detection methods and improved theoretical understanding. Dyson spheres or other massive engineering projects would create distinctive signatures in the infrared emissions from stars. Future surveys will monitor millions of stars simultaneously, looking for the thermal signatures that would indicate energy harvesting on astronomical scales. More subtle megastructures might also be detectable through their gravitational effects. Space-based interferometers, capable of detecting gravitational waves, might also be sensitive to the gravitational signatures of massive artificial structures. The regular movement of such structures could create detectable patterns in space-time itself. The development of new physics might also open unexpected avenues for detecting alien civilizations. If faster-than-light communication proves possible through manipulation of quantum fields or exotic matter, it might provide instantaneous contact across galactic distances. Technologies based on extra dimensions, dark matter interactions, or other advanced physics concepts might make detection and communication far easier than currently possible. Even our understanding of consciousness and intelligence continues to evolve, potentially affecting how we search for alien intelligence. If consciousness proves to be a quantum phenomenon that can exist independently of biological substrates, we might need to develop entirely new methods for detecting non-biological intelligence. The possibility of machine consciousness also affects our search strategies. If alien civilizations have transitioned to artificial intelligence, their activities and communications might be very different from what we expect from biological entities. Machine intelligences might have different goals, different timescales, and different methods of interaction that we're not prepared to recognize. The timeline for these advanced search capabilities varies widely depending on technological development and funding. Some improvements, like the Square Kilometre Array and Extremely Large Telescope, will come online within the next decade. Others, like interstellar missions and advanced AI systems, may require several decades or longer to reach full capability. However, the exponential pace of technological development suggests that capabilities we can barely imagine today might become routine within a few decades. The same exponential growth that has transformed computing, communications, and space technology over the past 50 years will likely continue, bringing capabilities that could revolutionize our search for alien intelligence. The philosophical implications of these future search capabilities are profound. If advanced alien civilizations exist and are detectable, our improved methods should eventually find evidence of them. The failure to detect alien intelligence despite vastly improved capabilities would strengthen arguments that we are alone or nearly alone in the galaxy. Conversely, the discovery of alien intelligence would transform human civilization in ways we can barely anticipate. Knowing that we are not alone would fundamentally change our perspective on our place in the universe. Contact with alien intelligence could accelerate our own technological and social development, providing new knowledge and new perspectives on the challenges facing our species. The possibility of discovering alien intelligence also raises important questions about how we should prepare for such contact. International protocols for announcing and responding to the discovery of alien intelligence are still rudimentary. As our detection capabilities improve, we need to develop more sophisticated frameworks for managing the discovery and potential communication with alien civilizations. The search for extraterrestrial intelligence represents one of the most important scientific endeavors of our time. Whether we find evidence of alien life or confirm that we are alone, the answer will profoundly affect our understanding of life, intelligence, and our cosmic significance. The technologies we're developing to conduct this search are already advancing human knowledge and capability in numerous fields. As we look toward the future, we can be confident that our search capabilities will continue to improve dramatically. Within the next few decades, we will have tools and methods that far exceed anything available today. Whether these tools will finally answer the question of whether we are alone remains to be seen, but they will certainly bring us closer to understanding our place in the cosmic community. The search itself has value beyond its ultimate success or failure. It pushes us to develop new technologies, to think more clearly about the nature of life and intelligence, and to consider our responsibilities as a potentially unique or potentially common form of consciousness in the universe. Whether we eventually make contact with alien intelligence or confirm our cosmic solitude, the search will have made us more capable, more knowledgeable, and more aware of the remarkable nature of existence itself. In the coming decades, as our tools become more powerful and our methods more sophisticated, we will finally begin to answer one of humanity's most fundamental questions. The universe will reveal whether we are alone or part of a vast community of intelligent beings. Either answer will transform our understanding of ourselves and our place among the stars.